Thanks. Hey, so I want to tell you about a surprising technique that came up as part of some work I did making an unobtrusive memory profiler. And just as a quick disclaimer, just because of the time limit, I'm going to be super Linux specific, and I'm going to omit a bunch of really interesting complications like threads and tail calls and things like that. But I'm really happy to talk about those things afterwards, so please track me down. So what do I mean by unobtrusive? This is kind of an idea I got into some years ago working on systems that were so sensitive to latency variations that a lot of conventional observation tools would just cause them to collapse. And tools like GDB and strace tend to use this API called ptrace for inspecting and controlling programs. And the thing about ptrace is that in order to get a consistent view of the program state, it tends to have to stop the program during that period of time. And those pauses were just too large for this poor system to handle. So I got interested in relaxations of that consistency and how I could still use sort of partial and inexact information to get useful measurements. And there are some great APIs in Linux like perf events and process VM readv and others that are super useful for this. And I sort of wanted to advocate for inexact results because I find tools like this have a role not in providing absolute truth, but as hypothesis generators. So there's this virtuous cycle where I measure safely but inexactly in production, and then that informs my mental model of how the system executes. And then I conduct exact experiments in a safe test environment and kind of reincorporate those changes into production and repeat. So that's the unobtrusive aspect. What about memory profiling? So I had been using a bunch of memory profiling tools that hook into malloc, the standard library allocator, and the problem with these, I noticed it tend to be blind to large allocations on the stack or other memory mappings. And so I wanted a memory profiler that would act more like a garbage collector, by which I mean that we identify the roots, which are locations from which pointers can originate, and then as long as we've got type information, we can just keep following those pointers until, in principle, we've walked all the live data in the program. And so where do these roots come from? So global variables, the program's registers, but it turned out that for the programs that I wanted to profile, I was looking at these long-lived allocations, and so the roots from which those things originated tend to be on the stack, and in particular towards the bottom, kind of the cold part of the stack. So how do we get the roots from the stack? Well, we have to first reconstruct the frames of the stack, and then debug information will tell us for each frame kind of what the types of old variables are there. But so just reconstructing the stack frames, normally we would do this with a backtrace. And I'm sure everyone here has run into a backtrace before, whether it's your code or someone else's code crashing. How do we produce that normally? So the program stops, we look at the registers. There are two that we really care about. There's the program counter, which tells us what instruction is executing, and the stack pointer that tells us where we are in the stack. And that's not enough information for us to unwind. So, well, it turns out there's actually a lot of controversy around unwind mechanisms still to this day, which is probably its own excellent Bang Bang Con talk. But I'm only going to talk about DWARF, which is kind of a fairly ubiquitous debugging format and unwind information. And what DWARF gives us is these call frame information records, or CFI. And though compactly encoded, what this effectively allows us to do is look up a program counter and figure out and get some expressions for computing old register values from the ones that we have. And kind of the most important one being what DWARF calls the canonical frame address, or CFA. And that is basically what the stack pointer was when this call was made. And once we've recovered that, we also can recover the program counter from the previous frame, right? Because it would have been pushed onto the stack right after this. And so we can basically just repeat that process all the way to the bottom of the stack. So that's how unwinding works normally. Now, there's a problem for my unobtrusive memory profiler, which is that if we don't stop the program while we're trying to read the stack, unless the program is blocked in a syscall the entire time, the top of the stack is just churning constantly, right? And we can use perf events to sample maybe a couple of pages of the stack safely, but in general, the kind of window of uncertainty can extend far beyond what we can safely sample. And if we just try and do a backtrace from the top of the stack, what I found is I typically just run into an obstacle somewhere in that window of uncertainty before I get down to the cold part of the stack where the delicious roots we seek are, right? So I asked myself, okay, could I reconstruct the stack frames from the bottom, at least the stack frames that I care about? And so we're using ELF binaries and ELF defines. The ELF header gives us an entry point that gives us an initial program counter, and procstat can tell us where the bottom of the stack is. So we have some of the register values we care about. Unfortunately, we can't just replay those dwarf CFI expressions in reverse. They're typically written as in terms of registers whose values we haven't reconstructed yet, right? But what we can do instead, so for each function, identify what calls it might make, right? And Dwarf has this DW tag call site that I thought would be super useful for this, but aside from identifying tail calls, I found I couldn't rely on it in general, so I had to disassemble the functions, which is not a big deal except on x86 where it's horrible, but still tractable. So once we have the call sites, places where a call might happen, we need to ask the question, was this call taken or not, right? And one of the things that we know is that if this call was taken, then the return address, the address of the instruction after that call, should be on the stack somewhere. And it turns out for a lot of functions just have fixed stack frame sizes, and if the frame pointer is omitted, then the dwarf CFI expressions are just these very simple constant offsets, and we already know the CFA because we're working from the bottom up. So for a lot of these functions, we can just do an exact match on the stack. Unfortunately, there are other functions, particularly those that allocate dynamically on the stack with alloca, things like that, where we might run into either a register whose value we haven't reconstructed yet, or some monstrosity. And I should mention that a big part of the controversy around dwarf, and something that's very surprising, is that dwarf expressions actually are specified in terms of a stack machine and can be, kind of quite complex computations. And so there's this real trade-off of that's very expressive, but there's some complexity and performance issues associated with that. But what I do for these cases, I just treat this as a wildcard match with kind of decreasing certainty of the interpretation of the stack the longer the match goes before we find something. And then we try and use the information in the next stack frame to corroborate whether our guess was correct or not. There's also the question of where these calls went. So lots of calls are just direct calls to immediates or PC relative values, but especially in dynamically linked programs, in object-oriented programs that make calls through vtables or jump tables, we'll find a lot of indirect calls through a register whose value we just haven't reconstructed yet. And this seemed like where I would definitely get stuck and have to throw in some heavy machinery like a SAT solver and abstract interpretation and data flow analysis. But I discovered that, at least for the programs that I cared about, a much simpler heuristic works quite well, which is that as I'm disassembling these functions, I'm also looking for memory references that are loading anything that looks like a pointer to an executable segment or a table thereof. And then when I encounter an indirect call, I just walk those from most recent to least recent, kind of decreasing certainty. And it turns out a lot of the times it will just be one of a handful of recently mentioned text pointers. So eventually we run out of call sites to check. We might actually have a couple of interpretations of the stack that are possible, but hopefully we got into the window of uncertainty. And so I take the deepest, most certain interpretation of the stack, and then from that I can reconstruct the roots that I care about. And you can imagine there are a lot of ways that programs could break this, but the surprising thing for me was that actually for the programs I cared about profiling, this worked. And that brings me to the moral of this talk, which is as programmers, we often face the impossible, right? And whether that's our beliefs or a rule we learned in school or a famous impossibility result from computer science. And I want to encourage you to, while remaining conscious of those things, entertain ideas about impossible problems, because even when general cases are impossible, there are often practical subsets for which we can write useful programs, or relaxations for which inexact values are still extremely useful. So don't let perfection get in the way of progress. Thank you.